Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 66. In today's lesson, we're going to be looking into binary search trees. So in the previous lesson, we looked at a binary tree, and it's basically a tree where each node has two possible options you can go to. We're going to see that the binary search tree takes advantage of that and does searching efficiently. So there's three operations we'll be concerned with. We'll be concerned with inserting a node into the tree, searching for a node in a tree, and deleting a node from a tree. The important thing to keep in mind with this is to make sure that you do a property. So as we go through it, we'll see that we want to keep the tree in a specific situation, and we'll see that binary search tree we're trying to make it efficient, but there's ways it can not be efficient. So we'll go ahead and get started with it. So I've created a new workspace. Let's create a text file because I feel like I'm going to want it. Let me add a new item. We'll call it trees.text. Just in case, but we'll see. So let's begin. So the primary, let me open the previous one as well. Let me just grab the tree for me at 1 second. So the important thing with a binary search tree is that for every node, the left subtree is greater than the right subtree. Here, I'll copy these lines. Here, not like that. Let me move this to the other group. There. All right, so there. I don't know if we need to pre-order, post-order. I'll leave it for the moment. So this one is a little harder to see without numbers, so we may switch this to numbers. Let's do this. Let's make this. Let's remove this. All right, let's make the root, let's say, we'll do it as 10. Let's do this one, let's say 5. Something between those two, 7, I guess. Something lower, 3. Something higher, 15. Something in between, 11. Something bigger, 20. We'll do something like that. Okay, so there's us a binary search tree. Here, let's delete 11 actually. There. So notice it's not completely full. So the tree we were dealing with yesterday, last lesson, we made sure it was full. So we did layer by layer. This one doesn't do that. So here the property is that every value to the left is less than the node. Every value to the right is greater than. And it holds true at this property. This side's less than, this side's greater than, and for every property in the tree. So that's the thing with a binary search tree. So let's say we add 11 and we just sort of seen where it would go. So you'd say, okay, we start at 10, insert. So which side? It's greater than 10, so it goes over here. Is it greater than 15? It is not, so it goes to the left child, and there's no left child, so you'd create one. Like that. So you can do insertions. There. You can do insertions. If you needed to do, let's say a 6. I'd have to think on that. I think it would go here. So what I think would happen is this. So we would do here. That might be the case to rebalance though. But I think that would work. So here, make sure that works. So 6 is less than 10, so it's on this side. 6 is greater than 5, so it's on this side. 6 is less than that. Yeah, I think that would work. Here, let me check. So here. So let's see what this one would do. So we have a binary search tree, so let's do this. Let's we'll insert the values we did. We'll do 10. We'll insert a 15. We'll insert 20. We'll insert 5. Insert a 7. Insert a 3. Insert an 11. Now let's see what it thinks we would do with a 6. Yep. So we don't try to rebalance it. So we'll see that there's we'll see that there's other structures that we will rebalance, but this one we're not going to. So you can grab this website. It's really good. It has some other great visualizations. So, or you can use that if you'd like. It's University of San Francisco. So we're going to do that today. Okay. So let's move on. So let's make a node. We'll need one like we did last time. So let's do public class. We'll do BST, binary search tree node. So public int, and we need a value. Public BST node left, and public BST node right. Now, it's fail. That should look pretty similar to the nodes from the binary search tree. So at each step for insert, we'll think of which side it goes on. So let's come up here. Let's do node insert. So let's look at the insert algorithm. And this should be nullable. In fact, these two should be. There. Okay. So let's see. So if node is null, return new BST node, passing in value equals value. So there's the null case. So now this is where we'll do the logic. So if value dot is less than node dot value, then node dot left. So if it's less than, it gets inserted to the left. Else if it's greater than node dot right equals insert to the right, return node. And I can put that in the else if I wanted to. So if it's equal, it's just already that node. So we're not allowing duplicates in this one. So if we do this pattern, so we insert a 10. So the node we insert in is null, so it's the first node. So let's do that. So let's do this. So BST node tree equals insert null and 10. static. We'll do it like that. So that gets us a tree, and then we'll do tree dot. We'll do insert tree, and let's do we'll do 5. Oh, I was going to do 15 next, so we could have done them in that order. And 3, 7, 6, 11, and 20. So that should get us our tree. Okay, let's grab these. So we'll put up traversals just so we can traverse this one. We'll have to adjust them ever so slightly. So we'll do BST node, BST node, BST node. All right, so there we go. So those are our algorithms from last time. So the post order, we get the value beforehand. The in order, we get it in the between, and post order at the end. All right, so let's see. So let's do this. So let's see the in order. I don't need to print in order tree. So let's see what we get. So what we should see is what? We should see 3, 5, 6, 7, 10, 11, 15, 20. So it should be a sorted order, right? So let's see if that runs. It did not. So 3, 5, 6, 10, 11, 15, and 20. It did right. Let's fix the printing just a little bit. Yeah, it worked better for letters. Let's do this. Let's just we'll just add a space. But I need to do it on post order. Or in order. All right, now let's take a look. Is it printing it as a space? Try one more. There. All right, so we get the sorted order. So if we remember from last lesson, that's actually what I mentioned is the in order sort should get us the sorted order, and it does. So interesting that works out. And we can see the others as well, but they won't be as interesting. CW pre-order. Being more trouble than I wanted. I should have just redesigned the methods probably. guess we want to do that. Then we'll copy. And then we'll do one more. This, and now we'll just grab them all and do post order. And what we're going to see is our in order is the interesting one here. Let's just take a look. And I needed to do a space here. Let's add that just to make it legible. All right, let's see. So the pre-order, it starts here, then here, then here, then it goes back, then here, here, and back, here, here, and then here. So I said if you drew a line around it, what you're doing is each time you come beside a node, so that the left side of the node, you hit a 10, a 5, 3, already hit 5, so 7, 6, all around, 15, 11, and 20. In order, you do it as you reach the bottom of the node. So 3, 5, 6, 7, 10, 11, 15, and 20. And post order as you get to the right side of the node. 3, 6, 7, 5, 11, 20, 15, and 10. So those worked out. So let's see. So that's inserting into the tree. So what happens if we insert something else? What if we insert in the already sorted order? What would happen? So we would do a 3, and we'd insert a 5. So it would go to the left, and then we'd insert a 6. It would go to the right. I said left, right. Then we'd insert a 7, right, 10, right, 11, right. And it's looking like a big line, so it looks like something like this. 3, 5, 6, 7, 10, 11, 15, and 20. And that'll look like if I drew it out as a tree with the lines in between, that would look a lot like a linked list. And that's what it would really be. And as we're going to see here in search, we lose our benefit at that point. So linked list, you have to search through each value. We're going to see here as we do search here next, that it's actually it's pretty easy, and what you get is a more performance search. So it's going to be very similar to the insert method. So let's go ahead and write it. So we'll do it's static full search. Node, and that should be nullable and value. So if node is null, return false. So if there's no tree, we're done. Else, if value is node.value, return true. That just equals there. So now, if value is less than node.value, return search node.left value, else return search node.right value. Yeah, let's add the braces so this one's a little more readable. There and there. I'm going to leave the other two as is, but I'll adjust that one. So what does this say? So if it's null, it's not equal. So there's no tree. So there can't be any values. If the value's equal, again, we're not allowing duplicates. So if the value's equal, that's the node you're looking for. You return true. Else, you go on the left side and keep trying if it's less than, or you go down the right side if it's greater than. So that'll get us a search. So let's say we're searching for 7. So we enter 7. So it's 10. The value is not null. The value is not 10. So then we go here. The value is less than 10. So we do search left. So now we have 5. 5 is not null. 5 is not the value. Okay, so now we say, is it less than 5? It is not. So we hit the else, and then we get 7. So now we say 7 null. It is not. The 7 equals 7. It does. So we were done. It's true. So there we go. So let's add another one. Let's look for 12. Okay, so we begin at 10. 10 does not equal 12. 12 is not less than the node, so we do the right side. Now we have 15. Is 15 null? It is not. Does 15 equal 12? It does not. Is the value less than 15? It is. So we check the left side. Now we get 11. So is 11 null? No. Is 11 equal to 12? No. Is 11 or is 12 less than 11? No. So we do the right side. The right side's null. So is null. So is the null? It is. So we did not find the value. So what this is basically a binary search. So here, if we needed to look for 12, and if we knew it was sorted, it would do 1, 2, 3, 4, 5, 6, 7. So there we didn't find 12, so we had to look through 7. Here, all we had to do was 1, 2, 3, 4. So what this is basically this gets you a binary search. And we see here the insertion, we're inserting in a similar fashion. So we're not gaining the full benefit of the linked list, but instead we're gaining something different. We don't have to do the insertion, but there is a little more logic here. But we don't have to go find where we're going to insert at. We just insert, and then it's okay, pass you down, and we're done. So that's not that hard, and both of these are it's relatively not that complex as far as the code goes. So the harder part is deleting. So what happens if we want to delete, let's say we want to delete 5, what happens here? So we want to say 5 goes away. Let me copy this. There. So what if we want to delete 5? What would we do? So here, let's start with this. Let's not start with 5. Let's do a leaf first. Let's delete 11. So what would we do? That's not terribly hard. We go here. We go till we find one with maybe we look at 15 and we say, okay, it should be on this side. Is this child 11 or 11? So maybe we just make that null. So we go till we find the node. And when we find it, so when we reach this value here, instead of returning true, we just set it to null. Maybe that would work. What happens if there's one child? So let's say we want to delete 7. So we go down 10, go down 5. Here's 7. We found 7. It does have a child, so a non-null side. But the other one's null. So at that point, we just say, okay, we just take the child and make that value, and the tree's property is still valid. 5 is greater, or 6 is greater than 5. If there's 2 children, though, so this was the original case, 5. Now what do we do? If we make it 3, sort of works out, actually. But if we make it 7, again, it sort of works out. What if we do? So that one just sort of works out. Whichever one of we could promote either one of these, and it would actually work out. Let's say we do 15 over here instead. Let's say we're deleting 15 maybe. So 15. So 20. 20 would work. So 20 would be valid. 11 wouldn't be, however. So why would an 11? So it's greater than 10. No, that would still work out. Okay, yeah, never mind. Yeah, actually that would work. So yeah, maybe I'm wrong. Maybe delete's not going to be that hard. So I guess what we could do is if we have the in order numbers, I guess you could pick the largest on the left subtree, maybe. Yeah, well, let's think. Let's code this through and let's see if we can find cases. I think that would be the case. You could pick that, or you could pick the smallest on the right side, maybe. So 6 here would be the best value, maybe. So 6, and then everything else is the same. So maybe that's the case. Let's try to implement it and let's see what happens. So let's see. We'll need a static method. Static. We'll return the tree probably. Delete. Int value. We'll try this. So let's see. So if node is null, return null. So if the null, or so at that point we're done, and we need to make this nullable, I guess. So let's see. So if value is less than node.value, then node.left equals delete node.left value. And right, we'll do the exact opposite. So else, let's do else if value is greater than node.value, node.right equals delete node.right value. Okay, so there's 2 of the cases. So the third case, what if it's equal? So else, so let's see. So if they're equal, then check the left side. Node.left is null. So if the left side's null, then we just return node.right. That one was easy. So if it's, I don't have a good example of that here, but we promote the only remaining child. That's not that hard. So here, if we, same thing on the other side, if node.right is null, return node.left. So basically promote the opposite. So the last case, what happens if there are 2 children? So let's see. We'll do BFT node. We'll do, let's do successor if I can spell. Equals, what do we want to do here? So let's do what I said. Let's try to promote the minimum on the right side, I think. So let's do that. So let's try this. Find min value, maybe something like that. We'll pass in node.write. Something like that maybe. So let's make that method. So static find minimum sub value. Yeah, something like this. So while node.left is not null, node equals node.left, return node. Right. So this shouldn't be the case. Okay, so we shouldn't need that, and that means we shouldn't need this. So the reason that's not the case is we checked right here. So we wouldn't want to use this outside of that. So let's do this. Let's make this an internal function. Yeah, let's do that. Let's make it that, and we'll return node here. I think that's right. So there. The reason I wanted to make it an internal function is I don't want to deal with this being potentially null. So this won't be null because we've checked if the left's null or the right's null. Neither one was null, so now right's not null. But it's a little hard to reason about that in general. So, and then here we're not returning a null value. So there, we'll find the minimum sub value. Now let's do this. So node dot value equals successor dot value. So swap the values, and then node dot write equals delete node dot write successor dot value. Yeah, I think that will work. So this is when you're starting to look. So let's say we're doing the 5 again. So start down the right side and continue down the right child and continue down its left children until you find the smallest value, in this case 6. Then make this one a 6. And then for its right side, go down and find it and delete it. So right, and then we go down the successor value. So now this is node 7. So not null. The node is 6 is less than 7. It is. So then we go on down left. We delete. So is 6 null? No. Is 6 less than node value? No. Is 6 greater than node value? 6? No. So it's here. So if the left tree is null, return the right tree. Is that right? Wait a minute. It'll return the right tree. Null. So deleted. Okay, yeah. So that makes sense. Yeah. So it comes down here, makes this null, and passes it back up to 7. And then 7's left child is then null. And then it returns 7. This one. Yeah, that should work. Yeah. So yeah, I think that works. So that's a little complex, and will take some grasping around to think about, but I think that works. So let's do this. Let's copy this once more. Let's try it with a 15 value. So start at 10. So we're looking for 15. So 10 is not null. Is the value less than? No. Is the value greater than? It is. So delete the right side. So go on to the right. So now we're there. So now node is 15. This is the value we're looking for. So it's not null. It's not less than. It is not greater than. So it must be equal to. Now, if the left side is null, it is not. If the right side is null, it is not. So we need to find a successor. All right. So we go down the right side. And there's only one value, so that's not going to be that hard. So while the left is not null, it is null immediately, so we just return 20. So node 20. So the value here gets to be 20. And then we delete the right side. So then we get 20, and it is not null. So is 20 that? No. Is 20 that? No. Else, if the left side is null, it is, then we return node.right. Node.right is also null. So that becomes null. That becomes null. We pass that back up to the parent, which is now 20 as well. We say, okay, we have no, this node is now null. So then we pass that up back to 10, and we return node. So we return 20, and we are done. So yeah, I think that works. So I believe that's the algorithm I've done before with this. So I guess the key takeaway here is that we're not directly replacing a node. We are swapping it with an easier value, and then deleting the easier value. I guess is what you could say is happening there. So let's do this. Let's hide the rest of these. We'll just concern ourselves with the pre-order. Let's see that happen here. So let's make sure we got this right. So we print it. Let's do delete tree, and let's delete we'll delete 5. So then let's do this again. All right, so delete 5. Let's do 15 because that's what we've got an example of. We'll do 15. Let's see what that looks like. So it should look like this at the end. Let's see if it does. This one. So 3, 5, 6, 7, 10, 11, 20. Looks correct to me. Let's do that again. Let's delete the 5 now. Three, 6. It promoted 6 properly. Yeah, that will. I think it did work. I think that worked as well. Now it looks like that. So 3, 6, 7, 10, 11, 20. I believe that worked out. What if we delete the root? If we delete the root, what happens? So it has both children. So this side will take precedence. Here, let's see that. This side will take precedence. So what happens? So as both children, it'll go find the smallest on the right side. So it'll go down here and then find this 11. So then it'll replace the 11. Then it'll delete the 11. So I think we'll get that. Let's see if we do. So now we get 3, 6, 7, 11, 20. Yes. So yeah, I believe we've got us a binary search tree at this point. Let's see. So we're up to 40 minutes. So let's see what else. I guess I didn't actually show an example of searching. Let's search for 11 here. Search tree 11. Now we'll do a 12 as well. Yeah, I don't guess we showed search. We just sort of walked through it, but Is there an 11? There is. Is there a 12? There is not. So yeah, I think that pretty close. So insert and search are pretty easy. Delete, I actually feel like that was actually straightforward, but it's because I already knew what I wanted to do here. I think there's something you can do on the other side as well, but I believe this is what I wanted to do, something like this. So the nice thing with all these operations, though, is that they're logarithmic. I don't have to search through the entire thing. It's a log of the tree. So it's log n on the average case. So for search, insert, and delete, it's average. We've seen here, though, if we insert and something's already sorted, that's when we can get into the worst case. And the worst case is all linear. So in the worst case, it's just a linked list. So a binary search tree is fast if it is valid. So if it stays valid here and it's balanced, so the balanced is, this is sort of balanced here. I'm trying to keep the layers as full as possible. So that's pretty good for what it is. Well, for the next lesson, let's we're going to look a little more into keeping it balanced. So there's additional tree structures that are designed to help with that. Well, two I've done are AVL and red black. So we may look at one of those two in the next lesson. Another one we've looked at already, we just didn't call it a tree, was a heap. And it works sort of similar to this as well, except you always have either the smallest or largest on top. So those will be probably where we end up going to in the near future. Maybe AVL. I actually haven't done it as recently, so maybe that should be the next one I'd try to do. But yeah, so that's a binary search tree. So we'll go ahead and call it here. So thanks for watching and have a wonderful rest of your day.